This is section 13.5b, part 3. And I first of all just want to say I'm sorry that my last video cut off so abruptly. I stopped to figure out what my mistake was, and instead of hitting pause, I accidentally hit quit. So let's fix that last little mistake before we go on. We had said, or I had set up the volume of the hemisphere with geometry and gotten 144 pi, which is correct. My mistake was actually earlier, and you guys probably already caught it. It was right here. 3 does not go into 216 36 times. In fact, 216 divided by 3 is 72. So my mental arithmetic was at fault. Calculator always wins, right? Then 2 times 72 would have given me 144 pi. And thank goodness that spherical integral really did work, otherwise we really would have been in trouble. All right, let's go ahead and move on. Our next example, example 3, has an integral that's already set up for us, but as you can imagine, we're probably not going to be happy with it. If you look at this, the exponential is x squared plus y squared plus z squared to the 3/2 power up there in the exponent. And I'm not at all happy with that because I can't integrate that with respect to x, y, or z by hand. I do notice, though, with that combination, x squared plus y squared plus z squared, spherical coordinates is sounding really good. That's just rho squared inside those parentheses. Additionally, both of my surfaces are spheres. So how nice is that, right? Let's go ahead and set this thing up. First of all, my region, my solid that I'm integrating over. This would be the sphere rho squared equals 9, or rho equals 3. And this one would be rho squared equals 16, or rho equals 4. So we are between rho equals 3 and rho equals 4. So I can't draw the whole solid because I'll just end up coloring over the whole thing, but basically we've got this three-dimensional shell. It's like a ball with a smaller ball cut out of the inside of it. All right, our integral. If we're going with spherical coordinates, I am going to change this exponent to rho squared inside the parentheses. And then I'm changing my dv into rho squared sine phi, d rho, d phi, d theta. As far as my limits of integration, if I draw that radial spoke starting from the origin out, this time I'm not in my region at rho equals 0. In fact, I don't enter it until right here at rho equal 3. I then exit my three-dimensional solid out here at rho equal 4. So there's the limits of integration on the rho. For phi, if I start up here at phi equals 0, I'm going to have to go all the way down to phi equal pi to cover this whole thing. If you then imagine taking this kind of a half circle I have here and rotating that all the way around, a whole 2 pi, that's going to create the entire spherical shell that we're talking about. So theta will go from 0 to 2 pi. Okay, I can use the theta trick. There's no thetas here except the d theta. So pull down a 2 pi for that. And what I've got here is e to the negative, multiplying those exponents, that just becomes a rho cubed. times the rho squared sine phi, d rho d phi d, just do rho d phi, sorry, I've already taken care of the d theta. Okay, a couple things here. This rho integral is now very doable, right? If u is equal to negative rho cubed, the derivative of that would be negative 3 rho squared, and I have the rho squared sitting right here. Alternatively, since my limits of integration now are just constants, if I wanted to, I could also switch the order of integration, and I would just have a sine phi to integrate by hand, and I could let the calculator do the slightly more complicated u substitution. Do whatever you want. Being ultimately on the lazy side, I guess, I'm going to do it the easy way. I'm going to switch my order of integration. So the rho integral from 3 to 4 is now on the outside, and the phi integral from 0 to pi is on the inside. And I'm integrating d phi first, and then d rho. So I'm still going to have this rho squared e to the minus rho cubed. Those are constant multipliers. And then the integral of sine phi is a negative cosine phi. I'll pull the negative out and put the cosine of, phi right there. I was one step ahead of myself, from 0 to pi. Cosine pi minus the same thing, cosine 0. Let's see, cosine of pi is -1, and cosine 0 is +1. So I just have a minus rho squared e to the negative rho cubed minus the exact same thing, or in other words, I have -2 rho squared e to the minus rho cubed d rho. And I'm going to do one more minor simplification. Pulling out that -2, I'd have 4 pi times this integral. Now, as we already talked about, that's very doable by hand, seeing as we do have a perfect u substitution set up here for us. However, I am going to use the calculator. Before I do, take a look at what's going to happen. When I do this integral, I'm going to end up plugging in values like 3 and 4, which are going to cause exponents of -27 or -64. This is going to be a very, very, very small number. So don't be surprised when the calculator gives us a tiny answer for this. In fact, I'm going to do this one with you just to show you what I mean. If I integrate from 3 to 4, and sorry, I just haven't bothered taking my calculator out of a polar mode, so it says theta instead of x or r or anything else, but all variables work the same, so no big deal. There we go. Notice I get this tiny little answer. Oftentimes we call that round-off error, but it's not this time. I was expecting a very small answer because of those large negative exponents on the e. So I'm going to keep this, 6.265 times 10 to the -13. And then if I multiply that by 4 pi, I have about 7.873 times 10 to the -12. So there's example 3. If we look at example 4, this time we have to set up our own integral. We're looking for the mass of the ice cream cone shape, bounded below by this cone and above by that sphere. given density function delta equals rho. So let's think about what this thing looks like. This is the lower bound, this cone. And the upper bound is the sphere with radius square root 8. I'm actually not going to draw the whole thing, I'm just going to draw part of it. The whole sphere would continue all the way around here. But I only want the part that's directly above the cone because I'm being bounded by both the cone and the sphere. So I want the part in between them, if that makes sense. So this is just that little piece of the sphere. The whole sphere would be all around here, right? But that's just that little piece of the sphere that ends up sitting right on top of or capping off the cone. All right, let's think about what those would look like. I do want to use spherical coordinates, and I know that for sure because my density function is already given in spherical coordinates. This is a sphere, which is great, and cones are usually pretty good as well. So let's think about what these equations would look like in spherical coordinates. The sphere itself is just rho squared equals 8, or rho equals the square root of 8, or 2 square root 2. To find the equation of the cone, I'm going to go back and use something that I mentioned to you I like to think about and use as a shortcut for finding these. With the cone, remember there was a whole bunch of algebra and trig that took to simplify this. But when my original cone had this form, I got it simplified down to the cotangent of phi equals that c value. I'm going to use that right now. In this case, the c value here is actually just 1. So if I say cotangent of phi equals 1, then the tangent of phi would be 1 over 1, or 1. And the inverse tangent of 1 is pi fourths. So the equation of that cone is phi equals pi fourths. All right, I think that's everything we need. Let's calculate our mass. To calculate mass, we always integrate the density function, which in this case is given as rho. And then I put in my dv, which is rho squared sine phi, d rho, d phi, d theta. If I imagine a radial spoke starting at the origin and going out, I'm already inside my object, my ice cream cone, right here from rho equals 0, and I'm always going to exit through the sphere itself. No matter where I draw, I'm going to go out through the sphere. I never go out through the cone. So the upper limit of integration for rho is rho equals 2 square root 2. Phi, I'm going to start here at phi equals 0, and then I'm going to continue to come on down until I reach the cone, which we've already said is at phi equals pi fourths. To get the entire ice cream cone, I would have to rotate that three-dimensionally all the way around the z-axis. So my theta is going to go from 0 to 2 pi again. And unless you're limiting yourself to a particular quadrant, that's pretty common, as we've seen. All right, to calculate this, I can pull down the 2 pi again. And let's see here. Yeah, this one's not too bad to integrate in the order that we're given. I'll just leave it this way this time. I really have rho cubed sine phi, d rho d phi. So we've got 2 pi, integral 0 to pi fourths, and then the integral of rho cubed would be 1/4 rho to the 4th I'm going to divide the 4 out here. And then I've got rho to the 4th sine phi, evaluated from rho equals 0 to rho equals 2 square root 2, with the d phi still waiting. That would simplify to pi halves. And let's see, rho to the 4th power, 2 square root 2 to the 4th power. Trust in my arithmetic now, so let me make sure I get it right. Is 64. Sine phi. And then when I plug in rho equals 0, that will just be 0. And if I do that integral on the calculator, let's see, I can't remember if I did that or not. I did. That turned out to be 18.745. Approximately. And then when I multiplied it by the pi over 2, I got a final answer of 29.445. And I can't remember here, they just gave us a density function, no units, so we're stuck with that as an answer. I don't have any units to put on it. All right, we will pause there and come back for one last example in the last video for this section.